All right, ladies and gentlemen, this is going to be another installment of our lectures for kinetics for AP Chemistry. This is lecture 5.4. This is Half-Life of First-Order Reactions. Our learning objective, something I need you to pay attention to because this is very specific, is that we want to be able to connect these half-life of our reactions to the rate constant of only a first-order reaction, right, and then justify it. There are half-lives for a second-order and a zero-order reaction. That stuff is in your book. I think it starts on page, what is this, 613 and 614 in your book if you want to read about the zero order and the second order half-lives for reactions. Probably I suggest you do that too. So we're going to start out and just review something here, right? My integrated rate law. We won't spend too much time because we already went over this, right? We take this equation where we've got rate equal to the rate law, and then we integrate that, and it gives us the first order integrated rate law, right? The graph of it has a negative slope, right, because of the negative k here. And then the y-intercept here would be my natural log of my initial concentration, or my starting concentration. Okay, because the first order integrated rate law graph has natural log on the y-axis, time on the x-axis. Okay, so that's all a review, right? And then now what we're going to do is we're going to introduce half-life. And so half-life is actually literally what it sounds like. It's half the life of a particular substance or chemical. And it's the amount of time it takes for half of the stuff to disappear. Now, this is actually a graph, right? And this is just like one that we've seen before where it's just simple concentration versus time. So simple concentration versus time. Notice this is not a straight line, right? This is not a straight line. So this is not a zero order reaction. Because think about what we went through just before here where we had just a straight concentration versus time. If it was a straight line, it would be a zero order reaction. But if it's concentration versus time, even remember back to my very first lecture of kinetics that the second order and the first order lines were actually curved. Okay? And so what we're going to do here is we're going to look and point out a couple of things. This particular area here, right, is a half-life because I go from 1 molar to 0.5 molar. Between these 2 points, half of my reactant disappears. And so this is my half-life. So my half-life in this particular case would be 100 seconds. All right, now take a look. My second half-life. So this is the first half-life is here. My second half-life is when I go from 0.5 to 0.250. So this is my half-life number 2. Notice it is still 100 seconds. And this is going to be something that is very unique to my first order reactions, is that they have a constant half-life. The half-life does not change. And it's concentration independent. So it doesn't depend on the concentration. The half-life does not depend on the concentration. All right, so, and that's even something I need to write down. So half-life of first order reactions is concentration. I'm going to say is not. How's that? Is not concentration dependent. Okay, and we'll see the math behind that here in just a second. So, but I need you to understand just conceptually what half-life is. If you're looking at a graph, how are you going to find half-life? And essentially all you're doing is you're looking for when does my concentration get cut in half. And I can continually go down and do this and, you know, smaller and smaller and smaller and smaller increments here. And so, but notice again, my third half-life is 100 seconds, my fourth half-life is 100 seconds, my fifth half-life is 100 seconds. That is something that is unique to first order reactions, okay? All right, so now what we're going to do is we're actually going to relate half-life to first order reactions. We're going to solve it out. So I've got a bunch of numbers here. I'm going to take you through this sequentially. All right, so this is where I'm starting, right? This is my first order integrated rate law. And so first off, I'm going to go and I'm going to change it back to here. And now this is something that you guys could have actually done, whether or not you know it. But remember, if I have like the natural log of A over B, and this I think is something from pre-cal or from algebra 2, that actually equals the natural log of A minus the natural log of B. All right, And so what we did is all we did to get from this point to this point is we subtracted this off, right? The natural log of a, we subtracted it off of both sides, so that we ended up with the natural log of a at some time minus the natural log of a initially, right? And so it's this term that combines to become that, right? And kt, negative kt, is just left over here on the side. All right, and now going from here to here, and it is important. I know y'all aren't really paying attention to the math probably, but you do need to know how to derive this equation. You need to know how to go from the first order rate law to, or the first order integrated rate law to the half-life equation to be able to prove that it is concentration independent. All right, and so now we're here at this protection. Whoops. We're here at this particular reaction, right? So we want to go from this step to this step, and we know we can go here to here because essentially for a half-life, we know that we're going to end up with half of our initial concentration, right? And so all I do is for A, right, going from here to here, I know that a T for a half-life is going to be 1/2 whatever I started out at, right? And so, that should be 0, and this should be T. So it should be 1/2 of whatever I started out with. So all I do is a simple substitution. So notice I end up with this. Now, once I'm at this point, something that you need to see is that these values actually cancel out. And so now it's where I get me to here, where I end up with the natural log of 1/2 equals negative kt. Well, one thing that we know is that the natural log of 1/2 is actually equal to negative 0.693. All right, and so essentially what we end up with, and I skipped a step here, right, going from here to here, we end up with negative 0.693 equals negative kt. And then all we do at that point, and this would be t to the half, by the way, once we get to this point, t to the half, because of what we substituted in right here. And so now we've got t to the half, and this is what we're concerned with because we want this half-life time. So I'm dividing off a negative k. So I divide off a negative k, divide off a negative k, right? The negatives here cancel out, and that's how I end up with my half-life equation for a first-order reaction. And again, notice my concentrations canceled out. And this is the only order reaction that the concentrations actually cancel out. And this is why my half-life for first-order reactions is concentration independent. It does not matter what the concentration you start at is. Your half-life is not determined by that. Okay? Very important for y'all to be able to mathematically determine this. All right, and so again, here we go. We've got this. This is my half-life equation that you're going to need to know. You need to understand that half-life is independent of the starting concentration, and so half-life time will be constant for your first-order reactions. Okay, and this isn't true again for the zero order and the second order. I think it'd probably take you about 10 minutes to read it in the book. I suggest you do that. I think it's on pages 613 and 614 in your book. And so I'd do that just to help with your understanding and concrete this stuff in or cement this stuff in. Okay, and remember, if you have any questions, write it down, and I'll see you in class.